All right, today we're going to talk about some hidden forces that are shaping, well, pretty much everything around us, from the blood flowing in your veins to the air rushing over a jet wing. See, it turns out that fluids kind of have two different personalities. One is super calm and orderly, and the other, it's completely wild and chaotic. Let's get into it.
You've seen this, right? You watch the smoke coming off a candle. For the first few inches, it's just this perfect, smooth, elegant stream going straight up. And then, bam! All of a sudden, it just explodes into this swirling, chaotic mess. Now, that's not random. That's actually a perfect, beautiful display of the two fundamental ways fluids can move. And that's exactly what we're breaking down today. So let's meet our two main characters here, laminar and turbulent flow. On the left, you've got laminar. Think of it as smooth, orderly. The fluid moves in these neat parallel layers, kind of like sliding a deck of cards. But on the right, you've got turbulent flow, and it is the total opposite. It's chaotic, it's swirling, it's full of these little whirlpools we call eddies that cause a ton of mixing. And by the way, that intense mixing, that's the only reason you can stir sugar into your coffee. Seriously, without turbulence, it'd just sit there at the bottom. So the big question is, how do we know which personality a fluid is going to show us? How can we actually predict if a flow is going to be smooth and laminar or just completely chaotic and turbulent? Well, luckily for us, engineers have a very specific tool for exactly that. And that tool is called the Reynolds number. It was developed by a brilliant scientist named Osborne Reynolds way back in 1883. It's just a single, really powerful number that kind of captures the entire essence of a flow and tells us what to expect.
Now don't let the formula scare you. It's really just a simple ratio. Think of it this way. Up top, in the numerator, you have all the things that want to cause a mess. The fluid's density, how fast it's moving, and some characteristic length, like the diameter of a pipe. And all of that is divided by the one thing on the bottom that's trying to keep the peace, the fluid's viscosity, which is basically just how thick or sludgy it is.
This really frames it perfectly. The Reynolds number is just a tug of war. On one side, you have inertial forces. That's the fluid's own momentum, and it's always pushing for chaos. On the other side, you have viscous forces, the fluid's internal friction, acting like a brake, trying to smooth things out and promote order.
And here's the result of that battle. When the Reynolds number is low, those orderly, viscous forces win the tug of war. The result? Smooth, predictable, laminar flow. But when that Reynolds number gets high enough, the chaotic, inertial forces totally take over, and the flow just flips into turbulence.
Okay, this is all fascinating theory, but why should you care? What does this actually mean in the real world? Well, let's look at the practical and sometimes life or death consequences of this difference.
Just picture water flowing through a regular pipe. If the flow is laminar, the velocity profile is this clean parabola shape. It's fastest right in the center and basically stops at the walls. But in turbulent flow? Nope. Those chaotic eddies mix everything up, and you get a much flatter, more uniform speed pretty much all the way across the pipe.
Now to push that fluid through the pipe, you need pressure to overcome the friction. For laminar flow, it's super straightforward. If you want to double the speed, you just double the pressure. It's a nice, simple, linear relationship.
But with turbulent flow, it is a completely different ballgame. The pressure you need is proportional to the velocity squared. Just let that sink in. You double the speed, you need 4 times the pressure. You triple the speed, you need 9 times the pressure. This is a huge deal and has massive implications for how much energy we use in everything from oil pipelines to our city water systems. And here's why this matters to every single one of us right now. Our blood flow, thank goodness, is mostly laminar. If it were turbulent, our hearts would have to work exponentially harder, 24/7, just to get blood around our bodies. Nature is an incredible engineer, and it designed our circulatory system to be as efficient as possible.
And to make things even crazier, turbulent flow is also super sensitive to other stuff, like how rough the inside of a pipe is. A rougher pipe means more friction and more wasted energy. But check this out. This is also why golf balls have dimples. Those little dimples actually force the air into a thin, turbulent layer right around the ball, which weirdly enough reduces the total drag and lets the ball fly way farther. It's a perfect example of using controlled chaos to your advantage.
All of this incredible complexity is why turbulence is still one of the great unsolved problems in classical physics. So how do engineers and scientists even begin to deal with it?
The real heart of the problem is something called the energy cascade. See, in a turbulent flow, you have these big, energy-packed eddies that break down into smaller ones,
and then those break down into even smaller ones, and on and on and on, until their energy finally just dissipates as heat. Trying to model this enormous range of sizes, from massive swirls down to microscopic ones, is just incredibly difficult.
So, to handle this, engineers use something called computational fluid dynamics, or CFD, and they have a few different ways of doing it. The absolute gold standard is DNS. It simulates everything, down to the tiniest little eddy. It's unbelievably accurate, but it can take a supercomputer months to run a single simulation. So a more practical compromise is LES, where you simulate the big, important eddies and just kind of estimate the small ones. But the real workhorse for most industries is RANS. It basically models the effects of all the eddies to give you an averaged-out result. It's the fastest and cheapest, but you lose all the beautiful, fine details of the chaos. It's always this constant trade-off between accuracy, cost, and time.
Maybe no one ever summarized this beautiful, chaotic dance better than the physicist Louis Fry Richardson with his famous little rhyme. It just perfectly captures that cascading nature of turbulence, this fundamental force that shapes everything from a tiny candle flame to the weather patterns on our entire planet, in ways we are still, to this day, trying to fully understand.